Okay, so we are back again. So far we have studied DC circuits, then single phase AC circuits, along with your what you call that resonance, as well as your maximum power transfer theorem we have seen, and also the three phase circuits. Now we'll start magnetic circuits, right? First thing is that magnetic circuit, you will find things are very simple. Only one or two things we have to understand, and rest you will find things are easy. Particularly in magnetic circuit means the coupling, right? So mutual coupling. So and we have to understand that, and you will find things are very easy. So just a magnetic circuit, actually the area around a magnet is called the magnetic field, right? That you know, and it is in this area that your what you call that the effect of the magnetic force produced by the magnet can be detected, right? So that is your now. And another thing is the electromagnetic system is an essential element of all rotating electric machines. In our electrical engineering we see, and electromechanical devices as well as static devices like transformer, right? So now magnetic field actually is a coupling medium allowing interchange of energy in either direction between electrical and mechanical system, right? So that is your what you call that your it is what is actually magnetic field. So next is your the magnetic effects of electric current. Now this is suppose here no is H is actually called magnetic field intensity or magnetic force. And first let me tell you, this is a conductor, right? This is a conductor, circular conductor, and plus means just try to understand that your flux line and this thing, right? This plus line means you take a paper and current is entering into the plane or into the paper, right? So if this is the direction of the current, if my thumb is the direction of the current, then this flux line will be curling, this curling finger, right? So this is the direction of the current. This plus means that your current is entering into on the paper, right? That means in the plane. And this direction, this is the direction of the flux. So if I say this current is entering into the plane, right, or in the paper, your notebook say it is entering, then this is the direction of the flux, right? That is clockwise direction, and that's why this one, that's why this is the flux line, and that's why this is the flux line. It is clockwise direction. This is actually right hand rule, right? So just we have to understand one or two few things, right? And this is and any from here to here, it is taken some distance r, right? This is your what you call the magnetic flux line. So H is actually magnetic field intensity, or sometimes we call magnetizing force, right? And your what you call, and this is r is to say later we will come to that r, it is radius, right? So in this case your just let me clear it. So then H actually it is uniform, this magnetic field is uniform around the conductor. So it is basically tangential to this point and it remains constant, right? So this is that your flux surrounding current, right? So a long straight conductor carrying current, it is whatever I said, it is written here, right, into the plane. The current causes a magnetic field to be established in the space you are surrounding it, right? A line of flux is a closed path around the current such that the magnetic force is tangential to its all point around the line. This is H, right? This is a H, right? H is the magnetic intensity or magnetizing force, right? So the direction of flux I told you, the right hand rule, I just explained you. You go through it, whatever I said, same thing. Everything is here. So now H defined as the causative current. We will come later. What is causative current? Per unit length of the flux line you are enclosing the current, right? Now in this case, because of symmetry, H is uniform along each flux line. So this is actually, if you look into that, this flux line is your concentric, right, and uniform. So H actually at every flux is tangential and uniform, right? So this is your what you call. So in this case, because of symmetry, H is uniform along each flux line. Since H is tangential all along a flux line for any flux line in radius r, right? So H is equal to I upon 2 pi r ampere per meter. That means this is the radius of a flux line r, say here in the diagram. This is the radius of the flux line your r, right? This is your radius of the flux line is r, right? And your this is uniform, it is circular. So it's a circumference is 2 pi r, that is actually length, length is equal to 2 pi r. Therefore, H is equal to, it will be I upon 2 pi r, it is ampere per meter, it is Ampere's law, right. So, let me clear it. So, this is actually your what you call H is equal to I upon 2 pi r, ampere per meter, that is Ampere's law. Now, the flux density B is established by this field intensity, right, is a property of the medium. So, for air or any non-magnetic medium, the ratio of magnetic flux density to magnetizing force is a constant. That is, if your B is the flux density, it is Tesla or Weber per meter square, its unit, right, and H, right, the magnetic field ampere per meter, or later we will see it is ampere turns per meter. That B by H is constant, that is flux density by magnetizing force ratio is always constant, right, and this constant is defined as mu 0. So, the permeability of free space or the magnetic space constant, right, it is called permeability of free space or the magnetic space constant, and mu 0 is equal to either 4 pi into 10 to the power minus 7 Weber per ampere meter, or it is Henry per meter, either this unit or this unit, Weber per ampere meter or Henry per meter. So, B is equal to mu 0 into H, B is the flux density, it is mu 0 into H and it is Weber per meter square or Tesla, its unit is, right. So, for all media other than free space, actually B is equal to mu 0 mu r into H, right. So, where mu r is the relative permeability and is defined as mu r is equal to flux density in the material divided by flux density in vacuum, right. So, it is a dimensionless quantity because numerator also flux density, denominator also flux density. So, it is basically dimensionless constant. So, flux density in material, so flux density in a vacuum. So, mu r varies with the type of magnetic material, and since it is a ratio of flux densities, I told you it has no unit, it is a dimensionless. Also, we can write that B is equal to mu into H, instead of mu 0 we can write mu into H in any material, right, your what you call in any particular your what you call in material. So, where mu is equal to mu 0 into mu r, it is called absolute permeability, right. So, mu is equal to mu 0 into your mu r, and the flux passing through the area for uniform flux density phi is equal to B into A. B is the flux density, suppose Weber per meter square, and A is the area, it is meter square. So, phi is equal to B into A, it is Weber, right. So, this is simple, these are all these simple formula, that B is equal to mu H, mu is equal to mu 0 mu r, and phi is equal to B into A. Now, magnetic circuits. Now, you consider, let us consider a toroidal ring of ferromagnetic material where mu greater than 1. It may be iron, it may be cobalt and nickel etc., right. So, it is considered a toroidal ring. Now, this is a circular ring. So, what we will do is, we will take your what you call that your mean path, this is actually mean flux path, we will take the mean distance, right. So, from here to here mean radius is capital R, right, and this is the core, circular core. So, its diameter is d, right, if its diameter is d, so area will be pi by 4 d square. If it is in meter, then it will be your meter square if d is in meter. This is that cross sectional area, right, this is circular one. This is the mean flux, your what you call mean your flux path. Now, let me clear it, let me move little bit up, right. Now, if you look into this, diagram, this is the coil wound on this your what you call on this toroidal ring. Now, current actually entering it, this current is entering, this ring has n number of turns, right. So, whenever, now here we have to understand your, I cannot revolve this 1 to 90 degree, I will tell you that the first thing is that this is the leakage flux path is also shown, and then this is the mean flux path. Now, question is that it is a coil, if you have a coil, you wrap the coil like this, right, you grasp the coil like this, and this is the current is entering, right, this is the current entering, this is the current, and finally the current is leaving. So, if you grasp the conductor like this, then this will be the direction of your mean flux path. This is the direction of the flux path, right? If I, for example, this is your what you call, if you grab it, this conductor, this coil, this, right, if you grab it like this, then this will be the direction of the flux path. So if I make it like this, so this, that's why this is my the direct, this is the, I mean in the direction of the current you grasp it, right, and then this thumb will be your direction of the flux path, right. So in this case, if you make it like this by right hand, if you grab this way your what you call this winding by right hand, then thumb will be the direction of the flux path. So this is the mean flux path, and there will be some leakage. So this line also shows some leakage flux path, right. So it is actually coming, it is actually direction will be like in the direction of the thumb if you grab it by right hand. So this is actually I and this is N turns, and this is the only thing need to understand, the direction of the flux path. So and this is we call mean flux path, because whatever core will take the your what you call the mean radius or mean length. Suppose for example, suppose from here, suppose the thickness of this one, suppose if you take your what you call thickness of this one, whatever it is, you take the mean path, you calculate from here to here the mean path, right, because we will go for mean your what you call, assuming that is uniform cross section. So we will follow the mean flux path. So this is my mean flux path. So direction of the your what you call flux line, later we will show you that is analogy to DC circuit voltage, current, resistance, to your what you call magnetic circuit, what are those quantity for analogous to that, right. So that means your this one, your the radius, mean radius are circular cross section, the diameter is d. So in this case the ring termed as core is excited by a coil on it with N turns carrying a current I told you, right. So that means the flux lines in the core enclose a current of Fm is equal to Ni, right. So this is actually, here it is number of turns is N, it is I, right. So your magnetizing force, or sometimes we call MMF, that is your Fm is equal to say Ni ampere turns, because I is ampere and N is turn. So its unit we call ampere turn. Now which is the causative current? I told you this causative current means cause of the existence of a magnetic flux in a magnetic circuit, right. That is why we call it is a causative current. So establishing this flux. So this is known as magnetometric force, sometimes we call it is MMF, right. So magnetometric force. So Fm is actually magnetometric force, sometimes we call it is as MMF. So by symmetry, H in this core is constant, because it is right around each flux line, and for the mean flux path, your mean flux line of radius capital R, the magnetizing force or magnetic intensity, right, it can be written as H is equal to Ni upon 2 pi r. Earlier we are writing I upon 2 pi r, but here you have n number of turns. So H is equal to Ni upon 2 pi r. So Ni is ampere turns and this is the length, so ampere turns per meter, and then Ni is equal to Fm. Here we have defined Fm is equal to Ni, right. So here you substitute, it will be Fm upon 2 pi r ampere turns per meter, or we can write H is equal to Fm upon L ampere turns per meter, that L is equal to actually length of the mean flux path, that is that circumference, that is your 2 pi r. So H is equal to Fm upon L, right. So next is the mean flux density. It is, we know B is equal to mu into H. So but H is equal to Fm upon L. So B is equal to mu into Fm upon L Weber per meter square or Tesla, either of these. This is the unit. Now flux is equal to A into B. A is the cross sectional area and B is the flux density. So A into B, that is B is equal to mu Fm upon L. So mu Fm upon L, right. So that means my phi is equal to, we can write Fm divided by L upon A mu, right, or we can write Fm upon R, or we can write is equal to P into Fm, right. So R actually we call L upon A mu m, it is ampere turns per Weber, its unit is, it is called reluctance of the magnetic circuit, right. This is called reluctance of the magnetic circuit, or P is equal to 1 upon R, it is called Weber per ampere turns, right. So here it is, R is actually ampere turns per Weber and P is the reciprocal of R, the reluctance, it will be just Weber, this unit will be Weber per ampere turns of this is called permeance of the magnetic circuit, right. So actually in the DC circuit, if you compare, that Fm actually like your what you call the voltage in DC circuit EMF, right? Here it is mmf. Now phi actually in DC circuit, say if it is a current, here analogous to magnetic circuit is a flux, and R is the resistance in DC circuit, whereas in your magnetic circuit is the reluctance, right? It is just a analogy to that, analogous to that, right? And permeance in the DC circuit, G is equal to 1 upon R, the conductance, here it is permeance, that is 1 upon R, that is Weber per ampere turn. So permeance of the magnetic circuit, right? So that means if I put it in a tabular form, that analogous thing, electrical circuit say EMF is E volt, in magnetic circuit in analogous is Fm, right? Current here is I ampere, in magnetic circuit in analogous is phi flux Weber. Now resistance R ohm in electric circuit, in for magnetic circuit is reluctance R, ampere turns per Weber or Henry, your reciprocal, right? Henry minus Henry to the power h to the power minus, that is 1 upon Henry, right? And current I is equal to E by R, that is EMF upon R, and here flux is equal to also, it is analogous to that Fm upon R, right? Because Fm is analogous to E and R reluctance R is analogous to resistance, so phi is equal to Fm upon R. So this is actually we call mmf upon reluctance, right? Here it is EMF upon resistance, here it is mmf upon reluctance, and R is equal to rho L upon A, right? In the case of reluctance, it is L upon A mu, right? So L upon A mu 0 mu R, mu is equal to mu. This is your what you call, this is the analogy from the electrical circuit and magnetic circuit. When you will solve the magnetic circuit, we will follow the same way, the way you do superposition or the way phi current. Here also we can draw the magnetic circuit and we can solve like this, right? So things are very simple. Only thing is that the right hand rule little bit you because we apply for various purposes the right hand rule. So because the polarity when you will make this magnetic equivalent circuit like electrical, you have to know which will be the plus, I mean analogous to your electrical circuit will be plus and which will be minus, that will actually from the right hand rule will determine, we will see that. So now if we make the DC circuit magnetic circuit like this, so this is Fm and this is phi, this is R. Actually how we have taken it, that if you come to this your what you call this this diagram, so if you look into that, if you look into that I told you grasp the conductor and thumb will be direction of the flux, right? So that means flux line is, suppose this is my flux line, this is my flux. So as it is direction, current actually leaves the positive terminal for your AC, your what you call for electric circuit, say DC circuit, right? For positive terminal, that your what you call for any take any voltage source, that current actually leaving the positive terminal, right? That means this is my plus and then this is my minus. So this will be my Fm. Fm is equal to this Ni, right? Your what you call by your what you call L, that is your ampere turns per meter. This is your, that means you have to see the which direction you have to take the flux. So if you grab the conductor, the flux is coming out, and then you put the reluctance and close the circuit, and this is your what you call the direction of the phi. So phi actually is equal to your, this is actually your Fm. So phi actually Fm upon your reluctance, right? And Fm is equal to Ni upon L. So whenever flux, I mean whenever you take in a direction, you see that flux is leaving like this, then this will be your plus, this is minus for analogous. But if you see in other way, if you see direction of the flux is like this, then this will be plus and this will be minus. This is the direction of the flux. Got it? I think you have got it, right? So this way we will make it. So once you understand this, you will find magnetic circuit is very simple, right? So that's why this circuit is drawn analogous to your say DC circuit, say this is analogous to DC circuit. So here phi is equal to Fm upon reluctance. So this way you can draw the circuit. Even we will see one or two problems that how to solve using this kind of circuit, right? So it is a DC circuit analogous of magnetic system, right? Next is, it is very simple thing, next is fringing. That is fringing flux, this is air gap, and this is one core, this is another core, in between some air gap is there. So it is actually, if you look into that, the flux density is not uniform, right? But particularly the corner, it is taking some different path, not directly going from this to that, right? It is taking some different path. So that means at an air gap in a magnetic core, right, the flux fringes out into neighboring area, neighboring air path as shown in figure 4. So it is like this, it is taking like this, right? So this is basically your nonlinear path, right. So, their being of reluctance comparable to that of the gap, right. The result is non-uniform flux density in the air gap, that is decreasing outward, right. So, that means decreasing, here it is outward. So, in that case your what you call your that is your enlargement of the effective air gap area and a decrease in the average gap your what you call average gap flux density. The fringing effect also disturbs the core flux pattern to some depth near the gap, right, and the effect of fringing increases with the air gap length. I mean this it depends on the length, right. So, I mean if it is suppose if this air gap length increases, the fringing effect also will increase. So, this although we will not study in detail for this course, we will not study this, just to give an idea that flux density is not uniform, right, and effective air because of this fringing effective air your area is getting decreases, right. So, this is called fringing. Now, next is the hysteresis loop. Here we have to understand something, what is hysteresis loop, because magnetic circuit we will see this one. So, hysteresis loop. So, magnetic we will see this or what you call hysteresis loop. Suppose this is in figure 5, it has been drawn. Now, suppose let a ferromagnetic material which is completely demagnetized, that is one in which B is equal to H is equal to 0. Now, generally if you want to make that if you want to completely demagnetize the ferromagnetic material, what you have to do is, before going to that figure, you have to make B is equal to H is equal to 0. That means I has to be 0. If H is equal to 0, I has to be 0, right. So, what you can do is, so this by making this B is equal to H is equal to 0, by reversing the magnetizing current, say I, a large number of times, while at the same time gradually reducing the current to 0. That means several times you have to reverse the direction of the your magnetizing current, I mean large number of times, and while at the same time gradually you have to reducing the current to 0, then only you will get B is equal to H is equal to 0 and be subject to your what you call be subjected to increasing values of magnetic field strength H, right, and the corresponding flux density be measured, right. So, in this case what will happen, that you have completely your what you call demagnetized that ferromagnetic material. So, that means it is starting from 0. Now, what you can do is that you are trying after making this, we are trying to increase the H, right. So, H will your what you call, if you H means you are increasing the current, right, you are increasing the current, then this one will follow the path OGB, right. So, in that case what will happen, that your H now increasing values of magnetic field strength H and the corresponding flux density be measured, right. So, that means you are increasing the H value now, I mean it is starting from the origin, that 0, because we have totally your what you call demagnetize the ferromagnetic material. Now, we are increasing the H, that means we are increasing the current I, say, right. So, in that case what will happen, after going on increasing the current, right, the domains actually begins to align and the resulting relationship between B and H is shown by the curve OGB, right. So, this is the curve OGB, right, this middle line, right, this middle your curve, that OGB, right. Suppose it has reached up to H. Now if you come to this, now at a particular value of H as shown in OI, most of the domains will be aligned and it becomes difficult to increase the flux density any further. The material is said to be saturated thus by the saturation flux density. That means this you are increasing, now current is increasing, you will reach a value that is OY, this is O and this is your Y, OY, right. So, after that even if you increase try to increase H max, that is I, you will find that flux density is not increasing. So, this is the maximum value after saturation, right, and this is your maximum flux density, and you can say this has been your what you call it is saturated. So, that is why it is written here that your what you call that after that flux density will not increase, the material is said to be saturated. Now, it is saturated, thus is by the saturation flux density Br. So, this is my H max and this is my B max, this is your what you call the B max, it is saturated, right. Now, question, and one thing is there, this Br do not read as saturated, right, it is actually later we will see it is actually be residual, right. So, anyway, we will come to that. So, this one, so just 1 minute, let me this thing, right. So, after that what you will do, that your now if the values of H is now reduce it, right, you try to reduce, it is found that flux density follows the curve BC, right. Now, when you try to reduce this, your what you call, try to reduce the current. Now, suppose I am moving in this reducing the current, so it is moving in this direction. So, you will find when H is equal to 0, some flux will be there in the material. This is actually called residual flux, right. So, this OC actually O to C, that is your BR, it is actually residual flux, right. So, although H is equal to 0, but some residual magnetism will be there. This is called your what you call that residual flux, right, and this is residual flux density. Now, further if you reverse the direction of the current, right, now this side you are moving, you will come to some point OD, right, that this point OD. So, some value of there will be there in the reverse direction, that H value, or you are reversing the direction of the current. At that time you will find that this value, your what you call this flux density, right, this value you are slowly and slowly coming to 0. At that time you will find B is equal to 0 at this point, right. So, what is happening, first it is we are from here we are increasing thing, it will reach to the saturation, so we call saturation flux density, then this is your B max, then we are reversing the direction of the current. When we are reversing the direction, that means current is decreasing now, current is we are decreasing, not reversing, we are decreasing the current. So, here at this point it will come, some residual flux will be there. Further we are reversing the direction of the current. So, it will come to this portion where you will get H value will be negative, and you will find your flux density B at this point is 0, right. Same philosophy will happen if you further go on your what you call that your increase the current in the negative direction, I mean this thing, the way it has reached here, same way it will reach, right, and it will get a point there, like your saturated point you will get there, and again further you are moving again in this direction, that again you are what you call your this negative current this side, you are slowly you are decreasing and coming to this point. So, some residual magnetism again will be here, and finally again after this point, same as before, it will come like this, and finally it will come like this. So, this way your BH loop will be completed, right. So, this is actually your what you call that your BH curve of a ferromagnetic material, right. So, this is what we have this thing, right, what we have understood this. There not much will just as is a magnetic circuit. So, we have to explain, we have to your what you call little bit understand on that. So, that means everything is given here, that from here it will start, but finally it will move like this, right. So, just step by step you go through whatever I have written here and whatever I have said, right, and that is the philosophy behind this, right. So, here also everything is whatever I said, everything is written here, right. And one thing is there, magnetic field strength, that is OD, required to remove the residual magnetism is called coercive force, right. So, this I mean this value actually this is the value, this is OD, this is that your OD, this portion, right, this is your whatever field strength is required, right, to make the flux density 0, this OD is required, that is your H is equal to OD, this will be negative value, this is actually called coercive force, right. Let me clear it. So, this is actually this one, that magnetic field strength OD required to remove the residual magnetism is called the coercive force, right. So, hysteresis and eddy current losses. When magnetic materials undergo cyclic variation of flux density, right, hysteresis and eddy current power losses occur in them, which are together known as coal loss. Coal loss means hysteresis loss plus eddy current loss, right. We will see later in the single phase transformer after this topic. So, and appear in the form of heat, right. So, coal loss is important in determining temperature rise, rating and efficiency of transformer. We will see that, right. Machines and other your AC operated your what you call AC operated electromagnetic devices. So, now power loss on the account of hysteresis, actually it is an empirical formula, right, your kh into f into B max to the power n into your what you call V watts, right. So, your V is not the voltage, V is the volume of the material, right. So, kh is characteristic constant of your core material. N is equal to Steinmetz exponent, range 1.5 to 2.0, typical value is 1.6. So, it is called Steinmetz constant, right. And V is equal to volume of the material in meter cube. This V is actually meter cube volume, right. And F is equal to supply frequency is hertz. This is F in hertz, right. This is the formula for the your what you call for the your hysteresis loss, right. Similarly, for eddy current power loss is given by it is Ke F square Bmx square into V watt. For some material it can be derived, but here this is your what you call, we are not giving that derivation and other thing, just you keep it in your mind that K is F square V max square into V watt. So, K is the characteristic constant of the core, right. So, up to this your what you call that your regarding little bit on magnetic circuit. Now, next is magnetically coupled circuit. So, when two loops with or without contact between them affect each other through the magnetic field generated by one of them, they are said to be magnetically coupled, right. Suppose you have two loops with or without contact between them, but affect each other through the magnetic field generated by one of them, they are said to be magnetically coupled. Now, two loops are there. If one loop is carrying that your what you call that time varying current, and another loop that some flux will be to link some flux to the other coil, right, and they are said to be actually magnetically coupled. Now, mutual inductance. Now, when two inductors or coils, right, are in a close proximity to each other, the magnetic flux, we will see later in the circuit diagram, the magnetic flux caused by current in one coil links with the other coil, right, thereby inducing voltage in the later, right, and this phenomena is known as mutual inductance. That means, when two inductors or two coils are there, say in a close proximity to each other, the magnetic flux caused by current in one coil links with the other coil, thereby inducing voltage in the later. This phenomena is known as mutual inductance, right. So, for example, suppose this is a simple circuit, this current source is shown, say it is IT for easy understanding, and voltage across this is V, and this is the phi, right, that flux your what you call, this is a time varying your what you call time varying current, and this is the flux phi, right, and it has number of your n turns. So, in your what you call the magnetic flux produced by a single coil with n turns. So, in this case also, if you your what you call that this is the your what you call, this is the direction of the your what you call direction of the flux, right, and this is your n turn. So, in that case what, according to Faraday's law, right, according to your Faraday's law, so your the voltage V induced in the coil is proportional to the number of turns n and the time rate of change of the magnitude of the flux. That is, we know the V is equal to n into d phi by dt, right. So, that means V is equal to n into d phi by dt, right. But question is that this phi, the flux phi is depends on the current I. If I decreases, phi will decrease. If I increases, phi will increase, right. So, this phi actually, that phi actually is a phi, or what you call it, say is a function of I. So, in that case what will happen that your, that means this equation, this n into d phi by dt, we can write as a chain rule, right. So, d phi by dt, we can write d phi by di into di by dt, right. So, it is d phi by di and di by dt. So, this term n d phi by di, this is actually L, the inductance, that means V is equal to L into di by dt, which you have seen earlier also, right. So, L into di by dt, and your L is equal to n into L is equal to n into d phi by di, right. Or in general sometimes we can write L, let me clear it, that means sometimes we write that your L is equal to, right, n phi by your I, that means L I is equal to n phi, right. This is also we require for numericals, that L I is equal to n phi. So, that means V is equal to L and L is equal to N into d phi. So, inductance of the coil commonly called as self inductance. So, this is actually self inductance for this kind of coil, and in here there is no other coil in the your what you call in the vicinity of this, right, no other coil. So, next is your, suppose this is the your what you call, this is your two coils in the your what you call mutual inductance M21 of coil 2 with respect to coil 1. Now, here a current source is I1t is there, this side it is not there. So, it is a only voltage here is measured V2 and two coils are there. So, if my total flux linkage, say my phi, say this is phi 1 for this coil 1, this is coil 1, this is my coil 1 and this is my coil 2, its inductance is L1, inductance is L2. So, the total flux is phi 1. So, phi 1 is the flux linkages your what you call your this coil 1, right. In addition to that, phi 1 to another part, right, it will phi 1 to also link coil 1 as well as your coil 2. This is actually mutual flux. So, the phi 1 is equal to your phi 1 plus phi 1 2. What actually you are doing? Phi 1 is the total flux, right, that links this your what you call links the coil 1, but phi 1 2 actually links the coil 2. This is your, this other part is linking the coil. So, phi 1 plus phi 1 2 links the coil 1 and phi 1 2 only it links the coil 2. So, phi 1 is equal to phi 1 plus phi 1 2, right, and whenever you say mutual, and number of turns of the coil 1 is N1 and number of the turns in coil is N2, right, and mutual inductance M21 means 2 means coil 2 with respect to coil 1. When you say M21, right, that means coil 1 is excited by some current I1, right, and that is the thing, and we are trying to find out the mutual inductance M21, that is this one M21. So, mutual inductance M21 of coil 2 with respect to coil 1. Whenever we write M21 means it is actually what we call mutual inductance of the coil 2 with respect to coil 1. This way you will read, right. So, this meaning of the suffix 21 is like that mutual inductance M21 whatever writing here with respect to your what we call a coil 2 with respect to coil 1, right. So, thank you very much, we will be back again.